Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the Monte Carlo method. Before we begin, I wanted to just give you a little bit of a motivation about it. The Monte Carlo method is extremely useful in practice because it turns out that for most realistic probabilistic models, or at least for many realistic probabilistic models, it is often impossible to estimate some of the probabilities that we're interested in, even if all the information we need is available. And this is for computational reasons, as we will see in a moment. So, in summary, life turns out to be not like a homework problem where, like in homework problems, you will give you the information, then you apply the chain rule, the law of total probability, you compute the probability that you're interested in. In real life, that's often impossible. So we have to resort to computer simulations in order to approximate the probabilities that we're interested in. And that's what the Monte Carlo method allows us to do. All right, so we're going to talk about Monte Carlo simulation. The motivation is that life is not a homework problem. And to see why, we're going to look at a specific probabilistic model that seeks to model the 3-on-3 basketball tournament that occurred in the 2021 Tokyo Olympics. So what we're going to do here is we're going to imagine that the Tokyo Olympics have not happened yet, and we want to predict the result of the 3-on-3 basketball tournament. We do know the participants. The participants were 8 countries: Belgium, China, Japan, Latvia, the Netherlands, Poland, the Russian Olympic Committee, and Serbia. What we want to do is to generate estimates of the probability that each of the teams win the gold medal, the silver medal, or the bronze medal. All right, so let's talk a little bit about how the tournament was organized. First, there was a group stage where every team played every other team. And then, according to the ranking from that group stage, there was a bracket. So the 2 top teams went directly to semifinals. The 2 bottom teams were eliminated, and the rest had to play each other in order to reach the semifinals. Okay, so that was the structure of the tournament. Now, in order to build a probabilistic model, we need some data. And the data that I decided to use were the ranking points for each of the players. So it turns out that in 3-on-3 basketball, each player gets awarded points after each game, and that allows us to rank them. So these points essentially quantify the performance of the player over the previous 12 months. Here is the ranking from before the Olympics. So you see that the best players are Serbian or Latvian, and these are their points. Okay. So now we need to convert those points to the probability that each team beats every other team so that we can predict the outcome of the tournament. We're going to use this very simple model that I came up with. I'm sure there are ways to improve it. Okay, but we're going to assume that it's good enough to give us some probabilities that we can use. So the idea is that we're going to say that the result of a game only depends on the total rating points of the team members of each team, and the probability that team A beats team B is equal to the total number of points of the players in team A divided by the sum of the points in the 2 teams. So if the 2 teams have the same number of points, this probability is going to be 1/2. If the players in team A have many more points than the players in team B, then the probability that A beats B is going to be very high. These are the ranking points for each of the teams that participated in the Olympics. So you see that Serbia and Latvia had a lot of points. They have very good players. And from using my formula, and again, we're going to just assume that this formula gives us the right probabilities, but I'm sure there are ways of improving it, and I encourage you to think how you would go, how you would improve it. Probably using some data from past games, but here we're not going to use data from past games. Okay, so according to this formula and the ranking points, the probability that Belgium beats Poland is roughly 1/2 because they have roughly the same number of points. The probability that China beats Serbia is extremely low because China has many, many less points than Serbia. And the probability that Latvia beats the Netherlands is pretty high because Latvia has many more points than the Netherlands. All right, so we're going to accept in our model that these probabilities are right, even though, as I said, they can probably be improved. All right, so now we have all the information we need. Okay, imagine that you want to compute the probability that Belgium wins bronze. And I encourage you to stop the video and think how you would go about estimating this probability. Well, what we should do is we compute all the possible ways in which Belgium can win bronze. For example, the ranking is Belgium first and then a certain order afterwards, and then the bracket gets played and Belgium loses in the semifinal but wins the game for bronze, okay, in a particular way. You have to actually, and this is very important, you have to specify all of the outcomes along the way, even for the other teams, and then you can compute the probability of that happening. And now you look at every other possible way in which Belgium ends up winning bronze. And then you just add the corresponding probabilities, okay? Something that I didn't say is that we're going to assume that the games are all independent. So we can just multiply the probabilities of each outcome in each game to get the probabilities of all of them happening. Okay, so hopefully that was clear. So is this easy to do? It's definitely easy to do, but it just takes a lot of time. Why? Because in total, so it's easy to do because we just need to check all the possible results in the tournament and see for which ones Belgium wins bronze, and then add up the probabilities corresponding to those specific results. And these probabilities, we can just compute them from the probabilities of each of the games. The problem is that we need to check a lot of results. So let's think how many results we need to check. If you kind of look at the bracket and look at the group stage and so on, there's a total of 40 games in the tournament. That also includes the game for the bronze medal. So that means that the possible different outcomes within the tournament are 2 to the 40. And 2 to the 40 is a lot. Okay, in particular is 1,000 billion. So, you know, with a good computer and some time, you can still actually do this for this tournament because it's a small tournament with just 8 teams. If you go to larger tournaments like Wimbledon or March Madness or the NBA, this is going to be becoming tractable very fast. Even though we have all the information, if we had like infinite time, we could, you know, like use the probabilities that we have to compute the probability that we're interested in. And again, this to me was kind of shocking as a student, but it happens all the time in realistic situations. And this is something that Stanislaw Ulam, I hope I'm not mispronouncing his name too badly, realized when he was trying to model a certain card game in 1946. So I'm going to read you what he wrote. This is from Wikipedia. After spending a lot of time trying to estimate these probabilities by pure combinatorial calculations, I wondered whether a more practical method than abstract thinking might not be to lay it out, say 100 times, and simply observe and count the number of successful plays. So essentially what he's saying is, if I try to start computing these probabilities by hand, there's just too many possibilities, they explode. Okay, in the case of our tournament, what happens is there's this exponential explosion of the outcomes that we have to keep track of when there are more teams in the tournament. So he encountered essentially the same situation for a card game, but then he said like, okay, but how about I just repeat, you know, the card game 100 times, and then I see how many times I get the outcome that I'm interested in, the event for which I want to estimate the probability. In our case, if we apply this reasoning, essentially what we would say is, okay, we have all the probabilities we need. We have the probability of every team beating every other team. How about we just simulate the tournament many, many, many times, and we see how often Belgium wins bronze, or you know, Serbia wins gold, or the Netherlands wins silver, and that will give us a reasonable estimate of the probability of that happening. And that's the Monte Carlo method. It's as simple as that. So if you realize, it's based on the intuitive definition of probability. When we were defining probability, what we were saying is that we intuitively, for us, probability is like the probability of an event is the fraction of times that the event happens if we repeat the experiment associated to the probability space many times. It just so happens that in reality, often, whatever we're modeling with our probability space will only happen once. For example, we're predicting the presidential election. But if we have our own model, which has these defined probabilities, for example, in the case of our tournament, we actually have the luxury to repeat, to sample from the model many times. And that's what we do when we apply the Monte Carlo method. And in practice, that's what people do when they, for example, in 538, when they estimate the probability that someone wins the presidential elections, they repeat the presidential election using probabilities that they have estimated from polls over and over, and then they see, what fraction of the times a certain candidate won within their simulations. So again, Monte Carlo simulations are used everywhere. So let's make things a little bit more precise. Imagine that we have a certain probability space and we want to estimate the probability that an event A happens. We assume that we can generate outcomes from the sample space according to the probability measure of interest. That's a very important assumption. If not, we cannot do this. And then what we do is we generate n simulated outcomes that are often called samples, a large number of them, and then we see how many of them end up in A. So again, as usual, this is an indicator function that is 1 if the sample is in the set of interest, in this case A, and 0 otherwise. So this fraction is the number of times that the outcome is in the event of interest. In our case, in our example with bronze and Belgium, like we simulate the tournament 10,000 times and we count how many of those times Belgium won bronze. Okay, and we divide again by the total number of simulations that we have carried out. Okay, so what happens if we do this with the probabilities that we get from my formula and from these ranking points? What happens is that Serbia wins gold roughly 43% of the time, Latvia 42%, the Russian Olympic Committee 6%, Belgium, the Netherlands 3%, Belgium 2%, Poland 2%, and China and Japan almost 0%. These are the probabilities of silver. And again, these are just the fraction of times over 10,000 simulations that, for example, Serbia won silver. Okay, you see again the probabilities, and bronze, in particular, the probability we were interested in is 11%. Okay, this is the probability that we couldn't compute just by hand, even though we had all the information. The Monte Carlo method allows us to compute it. Now let's take a look at the probabilities for the group of winning. So this is the probability of winning the group according to the model. We see that they're kind of similar to the gold medal game, although they're slightly higher, which kind of makes sense for the two main teams. I mean, Serbia and Latvia, and they're lower for the rest. This kind of makes sense because in the group stage, they're playing each other all the time. So it's more difficult for one of the good teams to just, if one of the good teams loses one game, it's not such a big deal. They won't get eliminated. They're going to play everyone else, so they can still finish first. Whereas afterwards in the bracket, if they lose, they're eliminated. That's it. So that's why these probabilities are slightly smaller, or at least that's my interpretation. The reason why I bring this up is that now I'm going to show you the real results, what happened in the tournament. What happened in the tournament is that Serbia won the group, but then they lost in the semifinals to the Russian Olympic Committee, and then Latvia beat the Russian Olympic Committee in the final. Okay, and Serbia ended up winning bronze. So those were the final results, and I would argue that the model does a reasonable job of estimating them. Of course, there's only one single outcome, so we can't really evaluate the model. We would have to evaluate the model over different competitions. Okay, well, I jumped very quickly. What about conditional probabilities? So we often want to estimate conditional probabilities. How do we apply Monte Carlo simulation to estimate conditional probabilities? Well, we go back to our intuitive definition of conditional probability. And if you remember, what we said is that the conditional probability of an event B given an event A is based again on repeating the experiment associated to the probability space many times, and then computing the fraction of times that both A and B occur out of the times that A occur. So essentially, we're just taking the simulated, the repetitions for which A happens, because we're conditioning on A, and we throw everything else away. And out of those repetitions where A happens, we see for how many of them B also happens. Okay, that's the intuitive definition of conditional probability. So based on that, if we want to estimate this conditional probability using Monte Carlo methods, well, we apply exactly the same idea. To approximate the probability of an event B conditioned on A, we again perform we again generate many simulated outcomes. But now when we compute the estimated probability that we're interested in, we only count the outcomes that were in A, and then we compute the fraction of how many out of those were also in B. Again, inspired by our intuitive understanding of what a conditional probability is. And that's it, okay? This is how we compute conditional probabilities. So let's apply it to our tournament example. Imagine that we want to estimate the probabilities of winning gold, of any team winning gold, if Serbia loses in the group stage. Okay, so I don't know, maybe two of them get injured, or they start fighting among each other or something like that, or they decide to pull out for political reasons. I don't know, something weird happens and Serbia loses is out in the group stage. Can we use our model to update our estimate of the probabilities that each of the teams wins gold? We can, right? We just apply Monte Carlo simulations. We do a lot of simulations. We only keep those in which Serbia gets eliminated in the group stage. And then we see out of those in how many cases did Latvia win, in how many cases did the Netherlands win, and so on. Okay, and this is what happens if we do this from 10,000 runs. Okay, so there is something seriously wrong with this procedure. And I want you to pause the video and think a little bit about it. Okay, so what could be the problem? Well, if you realize the probability that Serbia does not reach the bracket, this event that we're conditioning on has very, very low probability. So even though we have 10,000 simulations, in how many out of those is Serbia eliminated during the group stage? Only in 70. So these probabilities are computed essentially from 70, averaging over 70 data points. This is a very small number. And in general, Monte Carlo simulations are going to be accurate if you have a sufficient number of repetitions. So because of that, we cannot expect these estimated probabilities to be very accurate. And in fact, if we increase the number of runs to 1 million, the number of simulations that we perform, then we do get a reasonable number of times that Serbia is eliminated. And hence we get presumably more accurate probabilities. And you see that they're pretty different, right? Before we had that Belgium had a 10% of winning, but now it's just 6.5%. Now to check that indeed they are more accurate, we can increase the number of runs again to 10 million, and we see that the probabilities actually no longer change very much. Okay, so it turns out that Japan and China have roughly 1%, Belgium and Poland 6%, 8%, and then Latvia understandably has 63%. Okay, so the main beneficiaries from Serbia not reaching the bracket would be Latvia, but also the Russian Olympic Committee. Again, the nice things about probabilities is that they allow us to incorporate this information in a systematic way. All right, so what have we learned? We have learned that life is not a homework problem. Very often, even if you have all the necessary information, you will not be able to compute the probabilities that you're interested in exactly. However, Luckily, there's a solution to that, which is just to use simulations, in particular Monte Carlo simulations. However, you have to be careful because you need to have enough simulations to compute these fractions so that they are accurate. And in particular, rare events can be problematic. And that's all I got. Thank you very much.